3.1 Rates of Change and Tangents to Curves. The outline of this video is as follows. We will discuss the crucial difference between an average rate of change, which is like your average speed on a road trip, and an instantaneous rate of change, which is your speed at a single moment. To make this tangible, I will use Galileo's law of free fall as a guiding example, exploring how the speed of a falling object changes over time. From there, we will see how this idea of an instantaneous rate connects to a geometric problem, finding the slope of a curve at a single point by using a special line called a tangent line. Finally, I will introduce the foundational concept that ties all of these ideas together, which is the mathematical tool known as a limit. Understanding this progression is key to seeing how one powerful idea can solve problems in both physics and geometry. At its core, calculus is a powerful tool for understanding how a change in one quantity relates to a change in another. We see this everywhere in the world, from asking how a falling object's speed changes with each passing second, to figuring out how quickly the water level in a barrel rises as we add more liquid. To analyze these situations precisely, we will start by introducing two key ideas. The first is the average rate of change, which describes what happens over a period of time. The second is the instantaneous rate of change, which describes what happens at a single, specific moment. Investigating these two types of change will naturally lead us to the foundational concept of the entire course, which is the idea of a limit. So, our study of change begins here. To build our intuition for calculus, we will start with the physical example of an object in free fall and define the familiar concept of average speed. Galileo discovered that an object falling only under the influence of gravity travels a distance that is proportional to the square of the time it has been falling. We can express this using Galileo's law, where the distance fallen, which we call quay, is equal to about 4.9 times the time, t squared. Using this model, we can calculate an object's average speed over any time interval by dividing the total distance covered by the time that has elapsed. Mathematically, we write this as the ratio of the change in distance, or delta y, to the change in time, or delta t. It is important to remember this gives us the speed over an entire interval, not the speed at one specific instant. The key idea to remember is that average speed is a simple ratio of the change in position to the change in time. To get started, let us calculate the average speed of an object, which is a key idea for understanding rates of change. Average speed is defined as the total change in position divided by the total change in time. For a falling rock, we can model its position with the equation y equals 4.9 times t squared. To find the average speed during the first 2 seconds of its fall, we calculate the change in position, delta y, over the change in time, delta t. This gives us the fraction with a numerator of 4.9 times 2 squared and a denominator of 2, which simplifies to 9.8 meters per second. If we use a different interval, for example from 1 second to 2 seconds, the same calculation yields a faster average speed of 14.7 meters per second. This shows that average speed is not a single number, but depends entirely on the specific time interval you choose. So remember, average speed always describes motion over a duration, not at a single instant. To find the speed of an object at a single instant, which we will call time t0, we need a new approach. We know how to calculate average speed over an interval, but a single instant has 0 duration, which means the change in time is 0. Simply using the average speed formula would lead to division by 0, which is an undefined operation. So instead, we will calculate the average speed over a tiny time interval that starts at t0 and has a very short duration, which we will call h. For our falling rock, the average speed is given by the expression 4.9 times the quantity t0 plus h squared minus 4.9 times t0 squared, all divided by h. The key idea is to investigate what value this average speed approaches as the time interval AF gets closer and closer to zero. This process let us find the speed at a specific moment by looking at the trend over shrinking time intervals. To find the speed of an object at a single instant, we can analyze what happens to its average speed as the measurement interval becomes vanishingly small. While we cannot simply set our time interval, h, to zero in the average speed formula, we can observe a clear pattern as h gets progressively smaller. As we look at shorter and shorter intervals starting at 1 second, we see the calculated average speed gets closer and closer to a specific number, which we call a limiting value. For instance, the average speed for the falling rock approaches 9.8 meters per second at time equals 1, and 19.6 meters per second at time equals 2. This limiting value is what we formally define as the instantaneous speed at that exact moment. While the table of values gave us a strong hint, we can use algebra to find the exact instantaneous speed at 1 second. We begin with the average speed formula. Substituting t0 equals 1. After expanding the squared term in the numerator, the expression simplifies to 9.8 h plus 4.9 h squared, all divided by h. Because h represents a time interval that is approaching zero but is never actually zero, we can safely divide the numerator by h. This cancellation gives us a much simpler expression for the average speed, 9.8 plus 4.9 h. Now it is clear that as h gets closer and closer to zero, the term 4.9h also approaches zero, leaving us with a limiting value of exactly 9.8. Therefore, this calculation confirms that the instantaneous speed at 1 second is precisely 9.8 meters per second. Let us formalize the concept of an average rate of change for any function, as this is a foundational tool in calculus. The average rate of change measures how a function's output, which we call NIA, changes relative to its input, x, over a specific interval. We calculate this by taking the total change in y, written as delta y, and dividing it by the total change in x, or delta x. The first formula shows this as the fraction f of x2 minus f of x1, all over the quantity x2 minus x1. To make this notation simpler, we often call the length of the interval x2 minus x1, just h. This gives us the equivalent and very common formula, f of the quantity x plus h minus f of x, all divided by h, where h cannot be zero. Think of this like calculating average speed. If you travel 120 miles in 2 hours, your average rate is 60 miles per hour. What this formula really gives you is the slope of the straight line connecting 2 points on the function's graph. Now I will connect our formula for the average rate of change to a simple geometric idea, which makes it much easier to visualize. We can represent a function as a curve on a graph. If we choose 2 distinct points on this curve, say point P with coordinates x1 and f of x1, and point Q with coordinates x2 and f of x2, we can draw a straight line through them. A line that intersects a curve at 2 points is called a secant line. The slope of this secant line is calculated as the change in the vertical value divided by the change in the horizontal value between P and Q. This calculation is exactly the same as the formula for the average rate of change. Therefore, the essential thing to remember is that the average rate of change over an interval is visually represented by the slope of the secant line connecting that interval's endpoints. To understand how things change from moment to moment, we must first figure out how to define the slope of a curve at a single point. Unlike a straight line, which has a constant slope, a curve's steepness changes everywhere. Our approach is to define the slope of the curve at a specific point, P, as the slope of its tangent line. A tangent line is a line that just touches or skims the curve at that one point, similar to how a line can be tangent to a circle at a single spot. The main challenge, then, is to develop a precise method for calculating the slope of this tangent line for any general curve. This method is built upon the powerful mathematical idea of a limit. Therefore, to find the slope of a curve, we must first find the slope of its tangent line. To find the slope of a general curve at a single point, we use a powerful method that starts with what we can already calculate: the slope of a secant line. A secant line is simply a line that passes through two distinct points on the curve, which we can call P and Q. The core idea is to then investigate what happens to the slope of this secant line as we slide the point Q closer and closer to point P along the curve. We are looking for the limiting value that the slope approaches as the distance between P and Q shrinks to 0. If this limit exists, we formally define it to be the slope of the curve at point P. Therefore, the tangent line is the unique line passing through point P that has this exact slope. In short, the tangent line's slope is the limit of the secant line's slopes. Let us make this concrete by finding the slope of the parabola y equals x squared at the specific point P with coordinates 2, 4. To do this, I will pick a nearby point Q, whose x-coordinate is a small distance h away from 2. The slope of the secant line connecting P and Q is the change in y divided by the change in x. The calculation shows this is the fraction with the quantity 2 plus h squared minus 4 in the numerator, all over h. After we expand and simplify this expression, the slope of the secant line becomes simply 4 plus h, as long as h is not 0. Now for the key step. As the point Q gets infinitely close to P, the distance h approaches 0. When h approaches 0, our secant slope of 4 plus h approaches a limiting value of 4. Therefore, the slope of the tangent line to the parabola at the point 2, 4, is exactly 4. Now that we have found the slope of the tangent line, we can determine its complete equation, which gives us a linear model of the curve at that exact spot. To do this, we will use the point slope form, a standard way to write a line's equation from just one point and its slope. We know our specific point is P, with coordinates 2 and 4, and from our limit calculation, we know the slope m is exactly 4. We just substitute these values into the formula y minus y1 equals m times the quantity x minus x1. This gives us the equation y minus 4 equals 4 times the quantity x minus 2. By distributing the 4 on the right side and then adding 4 to both sides to solve for psi, we arrive at our final answer. The equation y equals 4 x minus 4 precisely defines the straight line tangent to our parabola at the point 2, 4. I want to introduce the fundamental connection between how a quantity changes and the geometry of its graph. We know that an average rate of change, like average speed, is calculated over an interval between two distinct points. Geometrically, this average rate is precisely the slope of the secant line, which is the line that passes through those 2 points on a curve. Now, to find the rate of change at a single instant, we need the instantaneous rate of change. We find this by imagining the 2 points for our secant line moving closer and closer until they effectively become one. The line that just touches the curve at that single point is the tangent line, and its slope gives us the instantaneous rate. For instance, the average speed of a falling rock is a secant slope, but its speed at a specific moment is a tangent slope. The essential idea is that average rates correspond to secant slopes, while instantaneous rates correspond to tangent slopes. Let us apply our concept of average rate of change to a real-world example: the growth of a fruit fly population. To find the average growth rate between 2 points in time, we calculate the slope of the secant line, which is a straight line connecting those 2 points on the curve. Our graph shows point P at day 23 with 150 flies, and point Q at day 45 with 340 flies. The change in population, or delta P, is 340 minus 150, giving us 190 flies. This occurred over a time interval, or delta T, of 45 minus 23, which is 22 days. Dividing the population change by the time interval gives an average growth of about 8.6 flies per day. Remember, this is the average across the entire 22-day period, not the specific rate on day 23 itself. The key takeaway is that the average rate of change is simply the slope of the secant line between your two data points. Let us begin by looking at how to measure change over an interval, using this fruit fly population as our guide. The average rate of change tells us how quickly a quantity changes, on average, between two specific points in time. To find this for the flies, we first calculate the change in population between day 23 and day 45, which is 340 minus 150, or 190 flies. Then we divide this by the change in time, which is 45 minus 23, or 22 days. This calculation gives us an average growth of about 8.6 flies per day. This value is visually represented by the slope of the secant line, which is the straight line connecting our 2 points on the curve. It is important to remember this is an average, not the growth rate on any single day. The key takeaway is that the slope of a secant line gives the average rate of change between 2 points. We have seen how to calculate an average growth rate over a time interval, but now we need to find the growth rate at a single, specific moment. The average rate we found from day 23 to day 45, for example, does not tell us how fast the population was growing precisely on day 23. To find this instantaneous rate of change, our strategy is to calculate the average rate over progressively smaller time intervals. We will keep our starting point P fixed at day 23, and then compute the slope of the secant line to a second point, Q. We then move this point Q closer and closer to P, for instance, from day 45 down to day 30. As the interval between P and Q shrinks, the slope of the secant line approaches a specific value. This limiting value represents the slope of the tangent line, which is the line that just touches the curve at our single point P. Therefore, the slope of the tangent line gives us the instantaneous rate of change at that exact moment. We can now connect the sequence of average rates to find the instantaneous rate of growth on day 23. Geometrically, as our time intervals became smaller, the secant lines rotated around point P and approached a single, unique line that just touches the curve at that point. We call this special line the tangent line, and its slope represents the instantaneous rate of change at that exact moment. To estimate this slope, we can pick 2 points that appear to be on the red tangent line, such as 14, 0 and 35, 350. The slope calculation is then the fraction 350 minus 0 over the quantity 35 minus 14, which is approximately 16.7. This means on day 23, the population was growing at about 16.7 flies per day. The essential idea to remember is that the slope of the tangent line gives the instantaneous rate of change at a single point. Here is a concrete example to help us visualize how sesicant slopes approach a tangent slope. My goal is to find the instantaneous growth rate of this fruit fly population at the single point P. To do this, I will start by calculating the average rate of change between P and a nearby point Q, which is just the slope of the blue secant line connecting them. Now, watch what happens as I choose points for Q that move closer and closer to P along the curve. The secant lines pivot, and their slopes change. The table on the right shows these slope values increasing from about 8.6 to 16.4, clearly getting closer to a single, limiting number. This limiting value is precisely the slope of the red tangent line at P. Therefore, the tangent slope represents the instantaneous rate of change at that specific moment. We will begin by exploring two fundamental ways to measure how a function changes: the average rate over an interval and the instantaneous rate at a single point. The average rate of change tells us how a function's output changes, on average, across an input interval of length h. We calculate this as the change in the function's value, which is f of the quantity x plus h minus f of x, all divided by h. Geometrically, this is simply the slope of the secant line connecting 2 points on the curve. To find the rate of change at one precise moment, we determine the instantaneous rate of change by taking the limit of this average rate as the interval length h approaches 0. For example, your average speed on a road trip is an average rate, while your speedometer reading is an instantaneous rate. This limiting process, which effectively turns a secant line into a tangent line, is a foundational concept in all of calculus. Let us pause here to review the core ideas we have just covered, which connect the geometry of a curve to its rate of change. The first question asks you to explain the fundamental difference between an average rate of change, which is the slope of a secant line connecting 2 points, and an instantaneous rate of change, which is the slope of the tangent line at a single point. The key is to describe how the concept of a limit provides the bridge between these two ideas. The second question then challenges you to apply this process algebraically to a specific function, the parabola defined by f of x equals 2x squared minus 1. You will first build the expression for the average rate of change, the difference quotient, and then you will calculate the limit as h approaches 0 to find the exact slope at the point where x equals 1. Working through these questions is an excellent way to confirm your understanding of this foundational concept. To wrap up, let us work through two questions that will help solidify your understanding of how we measure rates of change. The first question is conceptual, asking you to explain the geometric difference between an average rate of change, which is the slope of a secant line between 2 points, and an instantaneous rate of change, which is the slope of a tangent line at a single point. You will then describe how a limit is the essential tool that connects these two ideas. The second question provides a concrete function, f of x equals 2 times x squared minus 1, and asks you to perform the calculation. You will first set up and simplify the difference quotient for the average rate of change on the interval, from 1 to 1 plus each. Then, you will take the limit as each approaches 0 to find the precise instantaneous rate of change right at x equals 1. Completing these problems is the best way to confirm you understand how the limiting process defines the slope of a curve.